lab today?
No, no lab. Okay, so first of all, we skipped number 1. We're not going to be talking about our sample set, okay? And then 3 and 4, you could have done either by formula or by Venn diagram. So just look at those right there, and I'll let you check those there for a second. Check, because you need to be proficient in this skill, okay? We spent a day before that week off doing just Venn diagrams. I want you guys to get that. Okay. Now, your number 5 actually starts on the back of the next page. Mine started at the bottom of this page.
Can we do a vote?
Okay, so that's 31% for that part. And then 5B is 48%. 5C is 31%. Okay. I think your 9 should have been pretty straightforward. And you probably wrote these in percentages. Okay? Because in the past I had not required that, but I'm kind of making note of it now. So just translate mine into percentages, and that'll be what your answer is. And then for your number 10, okay, here's your number 10. I had to kind of write out here to the right what everything is, so I could keep straight, because I don't like keeping those numbers just random, floating out there in my head. I like to write them down so I can see them. Okay, so you may have done that. Okay. I don't know. What's the 3/7? Going to be almost half. Okay. Questions there? No. Yes. On B? Okay. On 10, do B and C. All right. So find the probability that the pet is a cat given that it's female. So that means that all the female are on the bottom. So all the female animals are on the bottom, which there were 28 female animals in total. And then the part that were cat females. See, the cat and female goes on top, and that was the 12. So that's how that's that. And then the bottom is going to be given that it's a dog. So I tell you it's a dog, so out of all the dogs, which there are 24 dogs, which ones are the female dogs? So female and dog, 16. Okay. Now, number 11 is very, very important, and I'm going to bridge number 11 into the concept that we're going to learn today. So, first, for number 11, it first asks about, just finding any man, the American male, the probability that he has both conditions. So that's out of 1. So out of 100%, find the probability that he has both conditions. So that's your 11%. Second one, what's the probability that a man, so out of your 100%, has high blood pressure? That means this entire section here. So that totals to 27%. The only requirement is that he has high blood pressure. He can have high cholesterol or he can have okay cholesterol. So both of those together. All right. Now, here's the part that's going to lead us into today. So C says, what's the probability that a man with high blood pressure has high cholesterol? So we are only pulling from the men with high blood pressure. So this is given that he has high blood pressure. Okay? So pull from all of the high blood pressure people, which is 27% of the group. Okay? And then, what's the probability that he also has high cholesterol? So, our formula means that then I have on top of the fraction the high cholesterol and the high blood pressure. So the high cholesterol and high blood pressure is this 0.11. Okay. So then that comes out to this 40.7%. And so here's what this is saying. Of all of the high blood pressure men, if you tell me they have high blood pressure, then there's a 40.7% chance, about a 41% chance that they also have high cholesterol. Okay? And so I want to talk about that right now. First, let's pretend like we got two guys. Okay, and these are our American men, and we're going to talk about high blood pressure and so on.
So, if one has high blood pressure,
Okay?
that means
Oh, I don't know how that works. Maybe, I don't know. I guess. Maybe, I don't know. Okay. So back to this. Look here. This guy on the left has high blood pressure. So I'm telling you he has high blood pressure. What's the probability that this guy also has high cholesterol? Look here. The guy has high blood pressure. What's the probability that he also has... no. That's the 40.7%. So this guy has a 40.7% chance. There's 40.7% chance that he has high cholesterol. Because I already know that he has high blood pressure. Now this guy, I don't know any qualities about him. I'm just going to be pulling him from all males. I don't know any other information about him. So, what's the probability that he has high cholesterol? Out of everybody, what's the probability that he has high cholesterol? Huh? Correct, that's this one. 32% of a chance of high cholesterol. So, look what has happened. Here's the key. Knowing that you have high blood pressure has done what to the chance of you having high cholesterol? Increased. So you would then say there's a relationship. There's a connection between high blood pressure and high cholesterol. You having high blood pressure increases the likelihood that you have high cholesterol. So they are related. Therefore, we would say that high blood pressure and high cholesterol are not independent of each other. If they were independent, then this number over here would be, I don't know, 35%. And this number over here would also be 35%. Okay? Sorry, I wrote that in this. If these two numbers were the same, then high blood pressure would have no effect on the likelihood of you having high cholesterol. If it has no effect, then they are independent of each other. If it's not changing the probability. But in this case, it is changing the probability, so it's independent. Not independent, yes. No, it's been fine. Oh, I know. Well, because I had decided to do that there. I know you're right. But then at one point I just well, I should just draw it over here. Okay. Let's finish this out. Okay, number 16 is the cost of repairing the pollution control system exceeds this 40% of the time. So, we know that when a driver takes his or her car in for inspection, what's the probability that he or she will end up paying more than $100 to repair? In order to have to do the repair, what's going to happen? They're going to have a faulty control. So that's 20% chance, and the 40% chance of that, or the 40% of that time that it's over $100. So this has to happen, and this has to happen simultaneously. Therefore, there's an 8% chance that when a person takes their car in, that they will not have, that they will have to repair it, and it'll cost over $100. All right. So then this number 21, we actually did not have this D because that pertains to what we're learning today. But a question: why are these two events not disjoint.
You would take either one that has a violation. Either one of them is correct. Some people do both.
That's the reason. The definition of disjoint, if something is disjoint, then they would have no outcomes in common. There would be nobody taking both. That's the definition of disjoint. But because 7% are taking both, then they have 7% of the outcomes in common, so therefore they are not disjoint. All right, now let's go to your notes and finish those things out. We've been working on those for a few days. Let's go ahead and finish out these. We're actually going to turn to the back of the first page to the number 10. So turn to the back of the first page to number 10. All right, here we go. The back of the first page, number 10. We actually did not do number 8 and 9, but we're going to do number 10 here real quick. So here we go. We want to state the formula used to determine whether or not two events are independent. Okay, we already talked about this when we just went over the homework. So let's see if we can't make a formula from that. On our homework, if this was true, then high blood pressure and high cholesterol would be independent. Look here. If the guy having high blood pressure had the same probability of high cholesterol as just any old guy having high cholesterol, if this number on the left and this number on the right are equal, then high cholesterol and high blood pressure would be considered independent. The reason would be, so if these two numbers were equal, the reason is because the fact that the guy had high blood pressure did not change the rate at which he has high cholesterol. If that were true, then the events would be independent. Did we find that to be the case on our homework? No, we did not. There was a difference. The left and the right side were not equal, so they were not independent. So let's make actually the formula for that. State the formula. And here it is. Probability of an event A, okay, given that B is happening, should equal the probability of A overall. If this is true, then two events are independent. And here's what that means. That in essence means that the fact that B happened did not change the probability of A happening. Probability of A on the left is the same as the probability of A on the right, regardless of whether B occurred or not. If B is not affecting it, it's not changing it, and then they're independent of each other. Okay. So, with that being said, on the back of the very last page, you have this question. And we're going to work through this one as an example of how you do a test for independence. Okay? That little formula, by the way, is not on your formula chart. That's one that you have to know. So I try to present it in a way that you can remember. Let's see if you can remember. What we want to do is the probability of being right-handed independent of gender. So, is the probability of being right-handed, given that you are a gender, I don't care which one you pick, what you want to say here. Pick a gender that's represented here. Thank you. Okay. Equals the probability of what would go right here. Right-handed goes right here. Here's why. This has to make common sense to you. I'm going to try to make that connection. Ready? This has to be the same as this. Whatever is here has to be the same as what's in front here, which implies that the fact that you are a male did not change it. Okay? You have to be able to pull that from your brain. It's not on a formula chart. So, now let's do this. Alright. So we know, given that it's male, all the males go on the bottom. How many males do we have? We have 52. Okay? And on the top, we want the right-handed males. Okay. We have the right-handed males. How many right-handed males are there? 43. Okay. If I did the math on that one, I think it's 82.7% of the males are right-handed. Okay. Next. What is the probability of right-handed overall? 87 out of overall is 100, so therefore this percent is 87%. So are those percentages the same? No, they are not the same. Therefore, right-handedness and gender are having an effect on one another. So they are not independent. You cannot say they are dependent, okay? Because that implies, like a direct relationship, and we can't say that's perfection for all situations. Dependent is a dirty word in statistics, okay? Right-handed and gender are not independent. But I want to go even further than that and say, if I know you are a male, then you are more or less likely to be right-handed. Less likely. If I know you're a male, given that you are a male, you are less likely to be right-handed than right-handedness overall. Then you are less likely to be right-handed than right-handedness overall. Boom. Okay? That's your example of how you do an independence check. Now, I do want to just tell you that if you had put some different variables up here, for example, if you had done this problem like this, probability of male given right-handed, then what would go here? Male. Okay? You could do this also, and your result would be the same in the end. Same conclusion. Okay? So you can pick the way that you design your things as long as they're in the right place. Okay, good. Now we're going to go to the second problem that you have there, which is this problem about Dr. Carey. And we're going to learn that in some problems you have way too many conditional statements. For example, in this case, Dr. Carey is really impaired and he has 2 bottles of sample pills that he often grabs a bottle without looking, and he takes the medicine. So, since the first bottle is closer to him, you have a 60% chance of grabbing it. He knows that the medicine from this bottle relieves him 70% of his pain 70% of the time, while the medicine in the other bottle relieves his pain 90% of the time. I don't know what I said. Hopefully I read what's here. I did not. I did not actually. So, 60% of the time, he grabs the first bottle. And of those times, his pain is relieved 70% of the time. Next, when he grabs the second bottle, his pain is relieved 90% of the time. So, here's the question. And I actually want you to write this and given that notation. What is the probability that Dr. Carey grabbed the first bottle, given that his pain was not relieved? Okay, I want you to write that question in this format. Okay, your question should look like this. What's the probability that he grabs the first bottle, given that his pain was not relieved? Now, according to our given that formula, this needs to be on the bottom of the fraction. Remember that? So what's on the bottom of the fraction is going to be the total probability. So you're going to have to figure out the total ways that the pain is not relieved. There's several different ways. What ways can his pain not be relieved? Picking the first bottle and not having relief, or picking the second bottle and not having relief. We're having multiple things. Because of that, a tree diagram is a way to organize these multiple conditions. So if you have a problem that says, well, if this, then that, and if this, then that. So if you have A lunch, then there's a 30% chance you picked milk. If you have B lunch, then there's a 60% chance that you have milk. And if you have C lunch, then there's a 40% chance you have milk. Whatever. When you have multiple conditions, organize it with a tree diagram. So let's do that. Here's Dr. Carey. He's sad because he has pain and because he's impaired since he just randomly picks stuff to take. So what's he going to do? He's going to pick a first bottle or he's going to pick the second bottle. And what's the probability that he picks that first bottle? 60% chance, which means how much percent of the time will he pick the second bottle? Okay. All right. Now, once he does that, then something else happens. What is it that happens? He either has relief or he has no relief. It's not 70% of his pain is relieved. He either has relief or no relief. Oh, really? I have the recording of it. We're going to go back to it and see. Okay? All right. So here, in the first bottle, 70% of the time he has relief, which then implies that 30% of the time he has no relief, because that's the 100%. That's all that can happen when he picks the first bottle. When he picks the second bottle, 90% of the time he will have relief, and 10% of the time he will have no relief, and that's all of the things that can happen. So, if I wrote this number, 0.6 times 0.7, what does that number tell you? Perfect. This number is the probability, or the percent of time, that he picks the first bottle and has relief. Then, this would be the percent of time that he picks the first bottle and has no relief. Okay, next, this would be the percent time that he picks the second bottle and has pain relief. And this would be the percent time that he picks the second bottle and has no pain relief. So if on my fraction up here, I want the total ways that his pain is not relieved, where are those values? What are those values? Not the first and the last. Where are the ways his pain is not relieved? This one, picking the first bottle and having no relief, plus picking the second bottle and having no relief. That would give you the total ways, the total percent chance that his pain is not relieved. So we would write this fraction as 0.6 times 0.3 plus 0.4 times 0.1, and that comes out to 0.22 on the bottom. Okay? I haven't addressed the top yet. According to our little question up here that we wrote, probability that he took the first bottle, given that his pain was not relieved, what information goes on top of our fraction? Well, like, don't give me the numbers. What concept goes on top? Good. First bottle and pain not relieved. Okay, so that's what I gotta find. And let me tell you something. This number up here on the top is always going to be a portion of the numbers on the bottom. So if you have, 4 sets of numbers on the bottom or whatever, the top number is always going to be one of those. So in this case, this is our total way of no relief. And which one of those portions am I interested in on the top? Grabbing the first bottle and not having relief. That's 0.18. That means 82%. Now, here is the thing that's left. I get incorrect interpretations of this number. And if you can't interpret what a number means, then what's the point of figuring out the number? Okay? There's no reason that you should go through the trouble of figuring out what that number is if you don't know what it means. So I'm going to give you 2 choices. Here's your choice number 1. I'll write it down, and then you got to think about it. Don't say out loud until I say, okay, what is it? So 82% of the time, Dr. Carey picks the first bottle and his pain is not relieved. Okay, that's choice number 1. Don't say anything. Here's choice number 2. 82% of the times Dr. Carey's pain is not relieved. He chose the first bottle. Okay, now, I want you to think about that. Those statements are very close, but one's correct and one's wrong. 82% of the time, Dr. Carey picks the first bottle and his pain is not relieved. Or, 82% of the time that Dr. Carey's pain is not relieved, he chose the first bottle. Question, what bag are you drawing from in this first statement? As far as what all's in the thing. The what? Sorry. Sorry. Hold on a second. That was just like a random question. But what I meant to say is 82% of the time. So this one you were choosing out of all time. What's the second one choosing out of? 82% of the what? That. Okay, so this is choosing out of the times the pain is not relieved. Are those different amounts? Yeah. Okay, what's the right answer? Statement 2 is correct. Because we did this out of the times that his pain is not relieved. Okay. By the way, the answer to the first statement is not 82% of the time. How much percent of the time does Dr. Carey pick the first bottle and his pain is not relieved? Look up here. That is this answer right here. Correct. That's that. He picked the first bottle and his pain is not relieved. That's the 18%. By the way, the fact that the 18% and the 82% are inverses, that's coincidence. Okay? So don't think there's a connection there. All right. Now, last thing I want to tell you what your homework actually is. So, if you look at your Chapter 15 homework, Part 2, you may omit 6, 8, 12, 14, and 19. In other words, you just need to do numbers, so you need to do numbers 24 to the end. Now, if you feel weak on this concept, you're welcome to do the other parts, and we will check them on Monday. Additionally, you need to do warm-up number 15, because we are going to be having your quiz 15 on Monday. All right? Now, we have time left in class. We have a good 20-something minutes. Okay? So, we have probably at least a solid 20 minutes. I want everybody to start on this warm-up. So we're all working on the same thing at start. I'm going to come around helping you. Okay? So, that's your assignment. 24 to the end on the homework part 2. And then the warm-up.